Hi everyone, my name is David Carabis. I'm a PhD candidate with the Mechanical Engineering Department here at RPI, and I'm one of several grad students who work with Professor John Wen in the robotics lab. My research is mainly focused on the robotic manipulation of large objects in space, so I'll take a little bit of time in this video to talk about that work here at RPI. We'll also show you a virtual demo from our lab, and finally take a little more time to talk about what it's like to be a grad student, how life is in Troy, and that sort of thing. My contact info is provided at the end of the video, so please feel free to contact me with any questions. We have several different projects being undertaken in the lab related to topics such as assistive care and manufacturing, so I also encourage you to check out videos from other grad students as well. Our group works with NASA Goddard in support of the Restore-L mission. This is a mission to send out a robotic satellite into space and do a semi-autonomous capture, docking, and refuel operation with a non-cooperative satellite. It's a really exciting project to be a part of, and it's one of my favorite things about being a grad student. I really love working on a problem that has some real world applications. There are a lot of challenges associated with this project. For one, there's a significant time delay in the video feed between these satellites and ground stations. This can make remote control, also known as teleoperation, really challenging. A good analogy is trying to play a video game with several seconds of lag, so you can imagine how difficult that is. Because of this, we're trying to develop autonomous and semi-autonomous operations that only require limited instruction from ground stations. Another challenge is the combination of large objects, such as satellites, and weak and flexible manipulator arms. Space arms tend to have a lot of joint flexibility in particular, and are often so weak they can't lift themselves up here on Earth. Of course, once you're in space, you can move massive objects with these arms if you move slowly, but this can create a lot of problems by generating oscillations or leading to collisions. Think of trying to pull a semi-truck along an ice rink. You might be able to get it going, but if you don't start to try and stop in time, you might get squished. My research is primarily focused on massive object manipulation, so I'm trying to answer questions such as how do you generate a trajectory for a robot arm in these scenarios, how do you undertake docking, how do you design controllers to mitigate oscillations, and how do you use onboard sensors such as a force sensor to do these operations with very limited human instruction. There are a lot of strategies to simulate space dynamics here on Earth. In our lab, we primarily use an air-bearing table and computer simulations. Our air-bearing table is shown here, and it's similar in principle to an air hockey table. The air-bearing object creates a thin film of air, which in turn creates a low-friction environment that approximates space dynamics in a plane. You can see the air-bearing object floating across the table here, so I give it a small push, and it'll continue rotating and translating as if it's out in space. Of course, this is a planar environment, so that is a bit of a drawback, but it is a really useful tool for conducting experiments. Here we can see some of our other work we did with onboard fan control, so we're trying to do station keeping here. This uses an onboard IMU to stop any disturbances, and you can see once I turn that off, the object rotates freely once again. We also use several robots in our work. Motoman is shown here. This is an industrial robot that is really accurate and has a high payload capacity. We use this when precise work is required. Here you can see it using visual and force feedback to track and grasp an air-bearing object. We also use the Baxter robot shown here. This robot is relatively weak. It can only lift about 5 pounds and has significant joint flexibility, so it's really a good stand-in for space manipulators. Finally, we use computer simulations to simulate the space environment as well. This video shows some of our trajectory generation results for manipulating a really large object in space. Next, I'd like to show you a virtual demo of some of our work. This demo shows a manipulation experiment on the air-bearing table, and the air-bearing object, which is about 14 kilograms and well beyond the Baxter's payload capacity, is tracked, captured, transported, and docked, much like we hope to do with an object in space. So first we have the tracking phase. So here the overhead camera is looking down at the kind of funny looking tag with black and white squares, and this lets the robot know the position and orientation of the air-bearing object. The robot can then track it and approach it, and then once it knows it's close enough, grasp the object. Next, we undergo a path and trajectory planning phase. So in this phase, our algorithm generates the arm trajectory to be executed. This then is displayed to a user, and then the user provides approval of the generated trajectory. And once that's done, the robot transports the captured object to the docking station, which we'll show here. Finally, we have the docking phase. Here the robot is using force and torque feedback to pull the object into the docking posts, ensuring the object is aligned correctly and sense when the docking posts have been contacted. Once everything is aligned and contact has been made, the docking clamps close autonomously. We also have a close-up shown here. This shows what happens when one docking post is contacted before the other. We use our force and torque feedback to rotate the object and make sure that everything is aligned correctly. Thanks for joining me on this virtual lab tour. Our future work is focused on developing a hybrid simulation where the Motorman robot is used to simulate an object in space while the Baxter acts as a stand-in for a space arm, and on docking in spatial scenarios. I'd like to take a few minutes to talk about my experience in grad school here at RPI. One thing to note as you transition from being an undergrad to a grad student is the shift of the focus from classes to research. So when you start out with a master's or in the master's portion of the program, you take a decent number of classes, but less than you would in undergrad, and then you add in some research. As you progress, especially if you're in a PhD program, you take less and less classes and do more and more research. I've really enjoyed that, so I do enjoy or have enjoyed all of the classes I've taken here at RPI, but I love our research project. I think it's really exciting, and that's really my favorite portion or part about the academics here at RPI is moving from taking classes, which have been great, to doing research, which I think is really exciting. I've also really enjoyed living in Troy, so we do experience all 4 seasons here, which I like, but that can be a little daunting if you're from a warmer climate. I really enjoy outdoor activities, so we're a short drive from the Adirondacks and the Catskills, so I do a lot of hiking during the warmer months. I also like to ski, and similarly, you can drive pretty close by. There's a few good mountains to ski on as well. Troy itself is also great. It's a small city, but it's up and coming, so there's a lot of good restaurants, and we have a couple of good local breweries as well. We also have a great farmers market, so if you visit or attend RPI, I really recommend checking it out. Thanks again for tuning in, and we hope to see you soon.